this lesson we're going to be talking about rates, ratios, and unit rate. So let's first start with the definition. The definition of a ratio. A ratio is a single value that compares two quantities, and it can be expressed with a colon, that's our symbol with two dots, the word to, or as a fraction. So there might be more ways to express information in a ratio than you might think. So let's look at the first example. The first example says Mr. Stewart's 10th period math class has 13 girls and 15 boys. Write every ratio that shows the boys and girls in Mr. Stewart's class. Now we're going to keep it simplified. If we unsimplified it, we would have an unlimited number of ratios. But one of the first ways we can talk about is 13 with the colon, 15. That's a ratio. We've got girls first and then boys. We could also write it with the word to. We could also write it as a fraction, 13 over 15. Those use kind of the three different formats, colon, the word to, or the fraction. But we could write other ratios, sharing similar information. We could reverse them, make it 15 colon 13. We could make it 15 to 13. We could make it 15 over 13. All right, well, where do we go from here? Well, let's think about the information in this problem. If we've got 13 girls and 15 boys, if we want to think about how many people are in the classroom, that would be 13 to 28, where this is the total. So the difference between the first 6 ratios that we did and this ratio is these ratios over here, what we would call part to part, because they were both pieces of the group. But this one would be now a part to whole. So the 28 is the whole class. Now we could rearrange this. We could rewrite this with the word to, and we could write this as a fraction. A fraction for this is probably more common because a part out of a whole, as this fraction looks, is a little bit more common. All right, so now we could reverse it. We could go 28 colon 13, 28 to 13, and 28 over 13. That's a little less common to see the fraction like this where the whole is on top. Then we could also describe it with the boys. We could go 15 colon 28, 15 to 28, or 15 over 28. And then finally we could flip it 28 to 15, 28 to, with a word, 15, and 28 over 15. So there's 18 different ways. While it's still simplified, somebody in the past years has talked about, well, we could talk about 26 to 30 as a ratio of boys to girls to boys. Yes, that's equivalent, but we could sit there and make equivalent ratios for the rest of time. Let's look at another example. In this example, talking about Mr. Janala's math class, he's got 15 girls and 10 boys, but it asks us to write the simplified ratios. We were kind of talking about that before. Now, 15 to 10, just like you might remember from working with the fractions, if we kind of like had this as a fraction, we could reduce this because both numbers are divisible by 5. We could reduce that to 3 to 2. So we're going to do all of our ratios here in this example with 3, 2, and the whole in this case would be 5 because that's 3 plus 2. So we could do 3 colon 2, 3 to 2, 3 over 2. We can reverse that to 2 colon 3, 2 to 3, 2 over 3. We can then go to the part to whole, 2 to 5, 2 with a word 2 to 5, 2 over 5. We can reverse it, 5 to 2, 5, the word 2 to 2, and 5 over 2. And then we can go with 3 to 5, 3, the word 2, 5, 3 over 5, and finally reversing that, 5 to 3, 5 to 3, or 5 over 3. Great, so there's 18 more ways. These are simplified. We took the original numbers and we brought them down to their lowest common numbers. Okay. Now, let's consider one of Mrs. Mitko's classes has 9 girls and 10 boys. Are there more girls in Mrs. Mitko's class or Mr. Stewart's class? Now, if you go back to look at Mr. Stewart's class, we remember that there were 13 girls. Now, if this was in first grade, I would expect you to think, oh, 13 girls is bigger than 9 girls, so clearly Mr. Stewart's class has more. But let's think a little bit deeper about this. More girls. What might be another way we could kind of interpret that? We might be really looking at how we are comparing the girls to the boys in class. So for instance, if there was some sort of competition in class, maybe it was who could solve the most math problems before the end of class, who would have a better chance of winning? The girls in Mrs. Mitko's class or the girls in Mr. Stewart's class? Assuming they're all, relatively the same ability, we need to think, is 9 versus 10 more fair, or is 13 more versus 15 more fair? What class would the girls fare better in? So we need a way that we could really compare them. So we could do this as a ratio in any of our forms, but you might be most familiar with looking at them as fractions. So I'm going to make a ratio in Mrs. Mitko's class, 9 over 10. This is girls to boys, girls over top of boys. And then we're going to do the same thing for Mr. Stewart's, 13 girls, 15 boys. Well, now they look like fractions. And I'm sure most of you have taken time in the past to compare fractions and determine which fraction is bigger. We can do the same thing here. The way that we'd like to compare fractions is to make their denominators the same. So what denominator could 10 and 15 both go into? They could both go into a denominator of 30. So if we change the 10 to a 30, we would have had to multiply by 3, so we're going to have to do that the same thing to the 9. So this would be a ratio of 27 to 30. That would be equivalent to Mrs. Mitko's class. Mr. Stewart's class, we'd have to multiply by 2 from 15 to get to 30. So we have to do the same thing to the 13 as well. So that's 26 to 30. So this now shows us that if there was 30 boys in both rooms, the girls in Mrs. Mitko's class would be equivalent to 27, versus in Mr. Stewart's class would it be only equivalent to 26. So we could kind of conclude that even though there is a greater number of girls in Mr. Stewart's class, the ratio of girls to boys is greater in Mrs. Mitko's class. All right, so that's a deeper explanation. That's really what we're going to be striving to look at, comparing ratios to figure out which one has a greater value of the ratio. Okay, so we can do the same thing here. One of Mrs. Yurkovich's classes had 10 girls and 8 boys. Are there more girls in Mrs. Yurkovich's class or Mr. Janala's class? So we're going to compare Mrs. Yurkovich here, which is a ratio 10 girls to 8 boys, and Mr. Janala's 15 to 10. So there's a couple different ways we could go about comparing them here. So I'm going to write Y for Yurkovich and G for Janala here. So in Yurkovich, we've got 10 over 8. And in Janala, we've got 15 over 10. We could do this very similar to the way we just did the last one. We could make these ratios with common denominators. So a common denominator for 8 and 10 would be 40. So Yurkovich, we'd have to multiply by 5 over 5, so now we're at 50 over 40. And for Janala, we had to multiply by 4 over 4, so now we're at 60 over 40. So now we see that if we made the boys both 40, that we would have a greater concentration of girls in Mr. Janala's class. So that is one way we could show this. Another way that we could kind of show these to be the same is, let's look at the numerators for a second. 10 and 15. We can make both of those numbers into 30. So this is saying if we kind of scaled up both rooms to have 30 girls, the same number of girls in each class, we'd have 30. Well, what do we do to Yurkovich's ratio? We multiplied that by 3. So that'd be the same as 24 boys. And for Mr. Janala's class, we multiplied by 2, so that would be 20 boys. So now you might be thinking, wait, is this telling me a different story here? Because this time, Yurkovich has kind of the higher numbers in the problem here. She's got 24 down there. Well, you need to think about what you're looking for. Here, this is saying there's more boys for the same number of girls. So more boys for the same number of girls would actually mean that the girls kind of have less strength. If they were doing that math competition, there'd be a less chance of them winning that because the boys have a greater ratio in there. So either way, these kind of look different. In this case, we made the boys the same, and here we made the girls the same. And both of those can lead us to concluding that Mr. Janala, make those separate, Janala's class has the higher ratio of girls. Great. Okay, now, that strategy where we made the boys the same or the girls the same worked great when we had two ratios that we were comparing. But let's look at the following example. It says, Jared goes to the grocery store looking to buy a cereal. His favorite cereal is sold in the following sizes and prices: 12 ounces for $3, 15 ounces for $4, and 22 ounces for $5.50, and 25 ounces for $6.50. So we've got 4 different ratios here that we're comparing, and to try to make them all the same, we're either going to end up with a really big number, or we're going to be comparing, back and forth over and over again. So let's look at a different strategy for how we might compare this. Now, most typically, when we're talking about price in a ratio, we're going to talk about price, the dollars, in our numerator of our fraction, and whatever other number is going to go in the bottom. So in this case, we're going to talk about number of ounces. So typically, it makes most sense to go with dollars per ounce, and that's going to be kind of the general convention that we go with. So if we start and we look at the first one has $3 per 12 ounce. So what does that turn into? We can turn that into what we call a unit rate. And if we actually go ahead and do the division here, we know that 3 divided by 12 is 0.25. So 0.25, this is the number of dollars, so $0.25 per ounce. And that's for 1 ounce, basically. Each 1 ounce is going to cost us 25 cents, or $0.25. It'd be the same as basically reducing this fraction. If we reduce this fraction to where we had 1 in the denominator, we would have 0.25 in our numerator. So this would be a ratio of 0.25 to 1. Well, let's do that same comparison for our other boxes of cereal. So we had 3 over 12. Let's also look at 4 divided by 15. And 4 divided by 15 turns out to be 0.26, and that 6 actually repeats. So you can put that bar over the repeating, over the 6 there, to say that it would keep going 6s forever. And that's $0.26 per ounce. I'll abbreviate this time. Okay, so right away, that's more dollars per ounce than the first box. And if you think about it, do you want to pay more money for every ounce of cereal? No. So right now, this is not a better deal than the first one. Well, let's keep going, see if we find any other better deals. So we've got $5.50 over 22. And if we simplify that, that turns out to be $0.25 per ounce. So that is actually the same as our first ratio. Even though they looked very different, they turned out to be equivalent to each other. Okay, let's do this one more time with our last box. And for our last box, we have $6.50, and we're dividing that by 25 ounces. Great. So when we go ahead and divide that, we start off, we get 0.25, but if we keep going one more place, it's 256. So if we actually had rounded up, it would be about 26 cents per ounce. So this one is, again, not the least expensive per ounce, so it's not the best rate. So we can actually conclude that the 12 ounce or the 22 ounce is the best deal. Now, I just want to show that there is a different strategy for going about this, kind of like we did last time. So, when we divided dollars per ounce, we got some messier numbers. If we had instead done ounces per dollar, we'd have got some nicer numbers here. So here we would have gotten 4 ounces per dollar. For here, 15 over 4, we would have gotten 3.75 ounces per dollar. And here, if we had done 22 over 550, we would have gotten, once again, 4 ounces per dollar. And lastly, if we had done 25 over 650, we would have gotten 3.85 ounces per dollar. Now, again, we kind of look at things backwards now. Do you want more ounces for every dollar or less ounce for every dollar? Well, you want more. If every dollar you spend, you want the most cereal. So here, the 4 ounces here and the 4 ounces here, that's the biggest number of ounces that we're getting for each dollar. The other two have less ounces for each dollar. So notice, in the red example here, ounces per dollar, we wanted the highest number, most ounces per dollar. But in the blue work, we wanted the least money per ounce. We don't want to spend that much. So you could go about this in two completely different approaches, but you have to keep in mind what you're looking for. Both of them conclude the same thing, that the 12 ounce or the 22 ounce is the best deal. So what we just did is we actually found a unit rate. A unit rate is a specific ratio that compares how many of a quantity corresponds with one of the second quantity. So we didn't write it every time, but this was per 1 ounce, and this was per $1. So it's however many of the one match up with just one of the other number. So that's called a unit rate. And we can use that especially when we're comparing more than two of a particular item. Okay, so let's look at a couple more examples. It says, for all the problems, express the situation as ratios with labels and answer the question to show your work. Okay, so Adam spent the weekend mowing 6 lawns and he was paid $120, while Peter only mowed 4 lawns for $100. Whose customers paid better, Adam or Peter? So if we think about this, there's two ways to do it. Let's start off with the dollars per lawn approach. And we think about it right away. Are we going to be looking for the higher or the lower dollars per lawn? Well, I want more money for all the work I'm doing. So we're going to look for the higher number. So 120 over 60 is going to give us 20. So over 1. So we can keep that as an equivalent ratio. If you want to put over the 1 to help remind yourself that now this is how much money he would get for 1 lawn. Great. And let's add some labels. This is money here per lawn. Great. So now that has some meaning. $20 per 1 lawn. And let's talk about, and we'll kind of add that this is Adam here. And then for Peter, Peter starts off with $100 per 4 lawns. And he then, if we reduce that, is $25 for 1 lawn. So whose customers paid better? It would be Peter's customers. Peter got $25 for each lawn, as opposed to Adam, who only got $20 per lawn. So Peter's customers paid better. Now, yes, Peter did mow less lawns. Adam earned more money on the weekend, but for the amount of work he did, Peter got kind of paid better. Okay, so in gym class, Danielle did 42 sit-ups in 60 seconds, and Erica did 55 sit-ups in 90 seconds. Now we could, get into a conversation about endurance, but let's fully compare who is better at sit-ups. So I'm going to write our two ratios. We've got 42 to 60 here, and I've got 55 to 90. So notice in the first example there, we kind of went with a unit rate approach. We found out how much per 1 lawn. I can tell right now that if I try to find a unit rate, I'm going to get some less than pleasant numbers. So I'm not going to choose that approach this time. I'm going to choose kind of a different approach where we make some of the numbers the same. We're comparing them in 60 seconds versus 90 seconds, and that's not a good way to figure out who's the best at sit-ups. So let's take Danielle. Let's say if they were both given the same amount of time. How many sit-ups would they be able to do? Well, what amount of time could we make them both into? Now, some of you might be able to right away immediately figure out 60 seconds and 90 seconds what would be the least common multiple. But if you're not, we just came from doing least common multiple in the last unit, so you could take a little second, make your little division ladder. All right, so let's see. Okay, I recognize right away that 10 goes in, so that'll leave me with 6 and 9. Okay, but I know there's still a 3 that goes in, and so that's going to leave me with 2 and 3. So we could find that the least common multiple is taking 10 times 3, which is 30, times 2, which is 60, times 3, which is 180. So that's going to be the common amount of time that works for both of them. Now, here's another trick of the division ladder. If you kind of look at the 60, if we kind of make some diagonals to the 3, the 60 needs to be multiplied by 3 to get to our least common multiple. The 90 needs to be multiplied by 2 to get to our least common multiple. So that's what's going to happen in our whole ratio here. This first ratio needs to be multiplied by 3. So if we take 42 and we multiply by 3, we're going to get 126. And if we take 55, we have to multiply this ratio by 2 because 90 times 2 is 180, so here we get 110. Okay, so this shows that if they were both given the same amount of time, 180 seconds, that Danielle would end up doing 16 more sit-ups. So Danielle, here, we see better at sit-ups, more sit-ups in the same amount of time. But, once again, that's not the only way we could have gone about this. We could have gone about this with the unit rate, and we could have gone about this with making even the number of sit-ups they did the same. If we made the number of sit-ups that they did the same, we'd be looking for the least amount of time. Now, looking at 42 and 55, that's going to be more work for ourselves. So you want to think ahead, where is going to be the best strategy? And this one, to me, the easiest and quickest thing would be, let's make 60 and 90 into a common number, in this case 180, and we can then say Danielle is better at sit-ups because she can do more in 180 seconds. Now, you could kind of elaborate, say that in real life maybe Danielle would start to get tired on the second 30 seconds, but from the information that we've gathered, Danielle seems to be doing sit-ups at a faster rate at least. Okay, so Samantha drove 150 miles in her car in 120 minutes, and Jack drove 100 miles in 75 minutes. Who drove faster? Okay, so let's try to do this without doing the unit rate first. So I'm going to put our 150, I'm going to do it as a fraction this time, right over 120. And I'm going to also set up 100 over 75. Okay, so let's turn these into some equivalent ratios. So 120 and 75, I could make those the same, but I can mentally make the numerators the same a little bit easier. So let's go ahead and make the numerators both into 300. Hopefully you can kind of quickly see that that would be the least common multiple of the numerators. So the denominator, so this fraction for the 150 over 120, Samantha's rate, we multiplied by 2. So this would be 240. So this means that she can drive 300 miles in 240 minutes. Jack, on the other hand, we had to multiply by 3. So 75 times 3 is 225. So what number are we looking for? Are we looking for the bigger number here, the bigger denominator here, or the smaller denominator? We have to think about what it really means. So 300 miles are both going the same distance. If we're looking for who drove faster, we want to know who drove that 300 miles in less time. So this instance, this was Jack over here. Jack drove 300 miles in less time, so his rate is faster. Great. So that's one way we can do it. And you could have totally compared the 75 and the 120 and made those the same. It just would have been a little bit messier work. Okay, so let's go ahead now. Let's also do unit rate. So we're going to go ahead and I'm going to go back to miles per hour, miles per minute here. So 150 over 120. So basically, we want to make this into something over 1. So we're going to go ahead and we divide those. So if we divide 150 by 120, we get 1.25. And often we could also just express that as 1.25, and that would be miles. And instead of writing per, you can write a slash, miles per minute. So that would be another way to write it. So that's 1.25 miles per minute. Let's then compare for Jack, who did 100 over 75. If we divide 100 by 75, we get 1.3, and that 3 repeats. And this is miles per minute. So here, are we looking for the bigger or the smaller value? Well, if it's per minute, that means per 1 minute. In 1 minute, who's going further? Well, once again, Jack. And you shouldn't have expected to get a different answer than part A. We just went about showing it in a different method. So Jack drives farther in 1 minute. So his rate is faster. Great. Okay, let's change gears a little bit. Let's talk a little bit just about writing ratios again. Here are some examples of what you might see. A bag of marbles contains 8 red, 16 blue, and 12 green marbles. Let's write a simplified part-to-whole ratio. First, let's starting with the green marbles. So let's think about the whole here for a second. The whole here, we've got 8 red, 12 green, that's 20, 16 more. So there's a total of 36 marbles. Okay, 36 marbles. So for green, green starts off 12 to 36. Now 12 to 36 is not simplified, so we can reduce that. We know 12 goes into both, so this is actually 1 to 3. So that, again, we're going to follow the same order. It tells us part, then whole, so we're going to keep it that way, 1, colon 3. And you could have written the word 2, you could have written 1 over 3. All of those would have been fine. Okay, now what about red marbles? Well, unsimplified, it would be 8 to our 36. Okay, we can recognize that 4 is going to go into both. So 4 goes into 8 twice, 4 goes into 36 9 times. So 2 to 9 is our simplified ratio for red marbles. And then for blue marbles, we have Start off with 16 to 36. All right, we can see 2 would go into both, 4 would go into both. 4 would reduce us to 4 to 9, and that would be our simplified ratio. Okay, now let's do a part-to-part ratio, and they give us both parts. So they give us green to red. Now, one thing to pay close attention to. The order that they write them in, green first, then red, is the order you must follow. So any question, if they ask and they give you the specific order of one ratio to another, make sure you keep yours in that same format. So we start off with green, which is 12, to red, which is 8. So we can simplify both of those by dividing by 4, and we get 3 to 2. So that's our simplified of green to red. Of red to blue, we start off 8 to 16. Well, 8 goes into both of those, so that's 1 to 2. And for blue to green, we would start off at 16 to 12. 4 goes into both of those, so that's 4 to 3. Great. All right. After playing 9 games in the basketball season, Beck had 54 points. Kevin played in 12 games and scored 70 points. Use your unit rate to compare Beck and Kevin. Okay, so if I'm thinking about a sports situation, we'd probably more commonly put points per game. So Beck has 54 points per game, points per 9 games, and then Kevin has 70 points per 12 game. Okay, so let's figure out what each of those is going to be per game. So 54 over 9 is 6, and that's points, and we can even write it as a fraction, points per game. That's another kind of way to write this. So 6 points per game for Beck. For Kevin, doesn't come out nice, but we could make that, we could just do that division. That's 5.83 points per game. So, who has the higher unit rate? In this case, Beck. Beck has the higher unit rate. Okay. Trying their best to finish the 25-book challenge, Ashley reads 11 books read 11 books in the last 15 weeks, and Nathan read 7 books in the last 10 weeks. Who is finishing books more quickly currently? So, if we look at Ashley, she read 11 in 15, and Nathan read 7 in 10. So again, we could find unit rates. That would require a calculator. If we didn't have a calculator ready and available to us, we could make these into fractions with equivalent denominators, common denominators. So we can make these both into something over 30. So the first fraction we'd have to double, so that'd be 22 over 30, and the second we'd have to triple, so that'd be 21 over 30. So Ashley versus Nathan, if they were both given 30 weeks, Ashley would finish 22 books. So Ashley would finish more books in 30 weeks. So her rate is faster. Great. Okay, lastly, we have another situation where we're doing some consumer shopping and we're trying to find the best deal. At the grocery store, Natalie sees a Coca-Cola sold in a variety of sizes. Which should she buy? So again, you don't have to do both methods, so I would pick a method that's going to work best for you. So let's go with dollars divided by ounce. That's the typical convention, and it makes sense that we want the least dollars per ounce. So if we do that, we're going to have to just basically go through each of these. So $1.80, if we divide that by 68 ounces, we get 0.026 dollars. I'm sure they put that up front. Dollars per ounce. If we look at the next package, it's $4.25 for 12 times 12. So that's really 144 ounces. So if we do that, we get 0.030, and that's dollars per ounce. For the 6-pack, that costs $4, and if we divide that by, that turns out to be 102 ounces if you take the 6 times the 17, and so that would give us $0.039 per ounce. And then lastly, we have an individual 1 liter for 95 cents, divided by its 34 ounces, and that gives us $0.028 per ounce. So these are really, we're talking here, this hundredths place is pennies. So they're all pretty close to 3 pennies. But if we want the least cost per ounce, the smallest price, we would be looking at this 2 liter for $1.80. So 2 liters, or the 2 liter bottle, for $1.80 is the best value. Terrific. So now that we've done this, you've gotten a good background on unit rate, ratio, and how to compare rates in a variety of different methods.